lecture number 3 in our series of industrial electronics. My name is Aaron Dolan and I'll be your instructor today. Today's a short class. We've got a long weekend coming up. However, I did want to go over a few things. First, let's review what we did in the lab. I want to introduce the concept of root mean squared. And I want to talk about mathematics, in particular trig. I'll give a very brief introduction because there are many other places you could go to find that information. But I want to tell you a story. I'll tell you my math story, the same one I've told several hundred people before. I think you'll like it, so stay tuned. In the lab, we worked with these DIN rail connected terminal blocks. And we connected red wires, we connected black wires, along with 3 motors. We made a series circuit and we made a parallel circuit. Let's do a quick review and see what that looks like. For the first part, you had an 18-volt power supply. Inside that power supply was an amp meter, and you had 3 motors. They were connected up like so. Again, these are DC motors, where the square box represents the brushes for the motor. This part of the lab was a series connection, where one followed right after the other. You may remember there was a red wire, black wire, red wire, black wire, red wire, black wire, and from the power supply there was a red wire leaving here and a black wire leaving there. So again, the trick with the series supply was to connect your motors up so that one was right after the other in a series connection like so. In an ideal, perfect world, this current meter would have read 200 milliamps, and each motor would have had, so the motor would have been about 6 volts. Again, that's an ideal world, and you certainly did not experience that in the lab. Instead, when you measured the voltage across each motor, right, you used 1 meter and you moved it a couple of times. When you measure the voltage on each motor, you might have gotten something like, oh, I don't know, 6 volts here and maybe 10 volts there and 2 volts there. In fact, this motor, for some of you, wasn't even turning. And what happened is, those were gear motors, and not all of those motors have the same friction in the gearbox. Not all the motors have the same design. So there's an imbalance, and some motors will drop more voltage across them than others. However, even though there was an imbalance, you'll notice that the sum of the voltages was still 18 volts. When you add them all up, you get 18 volts. That's actually one of the laws that we're going to talk about in the near future. It's called Kirchhoff's voltage law. So that's Kirchhoff's voltage law. And you might see that as KVL. And what it tells us is that if you were to travel around this circuit in a loop, right? If you were to travel the circuit in a loop and you were to add up all the voltages would equal 0. Another way of saying that is the supply voltage better equal the sum of the load voltages. And we did indeed see that in the lab. We then took our circuit apart and rebuilt it so it looks like this. Now we have a 6-volt supply. Here's that amp meter again. And then we have our 3 motors. And we called this the parallel connection. We did use a voltmeter. And we put that voltmeter right here. Actually, it didn't matter where we put the voltmeter. Everywhere we had the voltmeter, we measured 6 volts. And when you connected this up, all of the red wires connected together. So red, 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 and red from the power supply. And all the black wires connected together as well. So those were the negatives from the power supply. Recall there was the red terminal, the black terminal. Again, all the black wires connect together, all the red wires connected together in our parallel circuit. The performance for this parallel circuit was much better as far as the motors were concerned. In this circuit, the power supply makes sure that every motor has the same voltage, whereas with the series connection, the voltage was determined by the performance of the other motors. Not so here. Every motor has the same voltage. And when we measured the current, we saw that that was about 600 milliamps. And I asked you to make an assumption, and that assumption was that each motor was approximately equal, and that I, for motor 1, that's current, was the same as the current for motor 2, was the same as the current for motor 3. And in each case, the current on a motor was approximately 200 milliamps. The takeaway from the lab is that there are series and there are parallel circuits. There's also series parallel, but we'll worry about those another day. In a series circuit, all elements have the same current. In a parallel circuit, all elements have the same voltage. Over here, we would talk about the summation, that's the sigma symbol, of V load had better equal the voltage source. Or another way of saying that is with KVL. And we can talk about a closed loop. So there's your loop where the voltages equal 0. There is an equivalent over here. We'll talk about that another day. That's Kirchhoff's current law. It's a concept I wanted to introduce you to real quick. So let's do a quick sidebar. Let's suppose we have a direct current system. And on that direct current, there is a light bulb. So there's your symbol for a light bulb. Now suppose on the other side, we had the same light bulb, but this time the light bulb is driven not by a battery, but by an AC source. So this is direct current, and this is alternating current. If you were to observe the brightness of each bulb, right? If you were to look that way, and then you were to look that way, and I told you to adjust the power supplies so that they were equal brightness, something very interesting would happen. For sake of discussion, let's assume this voltage over here is 120 volts DC. And over here, we would have a sinusoidal voltage, because that's what AC is. Right? It looks something like that, as a function of time. And the question is, what do you set the AC to, right? What is this value right here? What is this V max and this negative V max? What values do those get set to in order to match the DC? Turns out that this value is 170 volts. So plus or minus 170 volts of that sinusoid is required to equate to 120 volts. Again, the observer is watching both light bulbs. We set the DC to 120. We adjust the AC till the bulbs have equal brightness, and this is what we find. We find 170 plus or minus. Here's the math for that. The voltage, new word, RMS, is equal to the peak voltage over the square root of 2. And in our case, we said that that peak voltage was 170 over the square root of 2. So VRMS, if we go to the calculator, 170 divided by the square root of 2 equals 120 volts. And that is our common household voltage that you see. In another class, we could talk about where this magic square root of 2 comes from, but in order to do that, we have to do calculus. So for our purposes in today, we're just going to remember this equation right here, which equates the peak voltage, right here, there's a peak voltage, there's a peak voltage, to the RMS value. All right. I owe you a bit of an explanation as to why we're bouncing around here. So this is the map of the class. We are right now talking about direct current. In the near future, we are going to be talking about alternating current. And this is one of the examples, right? This is an alternating current waveform. Later, we'll talk about motors. You are here today, and we will soon be here. And what I wanted to tell you is that when we get to AC, we need to know our trigonometry. What we're doing in this class today is we are trying to decouple the learning of trigonometry from the learning of AC. Because if we get here and we haven't reviewed trigonometry first, things are going to get pretty ugly. It's hard to do both at the same time. But by pulling that trigonometry back, we'll pull the trig back here, we'll be in a better position. Trigonometry in electronics. We'll start with a magnet. We'll put a curved face here and a curved face there. A little more curve. There we go. We'll call this the North Pole. We'll call this the South Pole. And there will be a magnetic flux across this gap. Into that gap, we will insert a coil that's free to pivot at this point here. So into that, we insert a coil that's free to pivot. We'll let it turn in this direction. And essentially what we've just done is we've created a generator. As we rotate that device around in the presence of the magnetic field, we generate a voltage. And that voltage has this form. If you've built the machine correctly, you could even end up with your household electricity, which is plus and minus 170 with a period, a frequency of 60 hertz. So that would be, if you wanted to get fussy, we would call this, the voltage as a function of time is 170, we'll call it cosine of 60 pi t. And that's a trigonometry function, where this is the peak voltage, and this is the frequency. While we're here, I want to show you something. So again, we have these two wires. I'm going to put a dot and then an X on them. I want to show you something. If we are here, and the position is like so, so when we are in this position, you'll find that the voltage is at a minimum. So we started here. When we rotate to this position, we'll find that the voltage is at a maximum. So that is this position here. There's the dot, there's the X. So that was a 90-degree rotation. So that was 90 degrees. After another 90 degrees, we end up here. So now the dot is pointing down. And there's the X there. So we've gone 180 degrees. Next, We are here. The dot is there with the x on this side. And finally, when we make the complete circle, when we make all 360 degrees, we are back where we started. So that's how, or that's what it would look like if we were to sweep this rotating member 360 degrees in the presence of a magnetic field. We sweep out a sinusoid that looks like that. We could certainly go on, and we will, but another day. That's enough for now. I want to take a hard break now and jump into trigonometry. Let's write down what we know for trigonometry. So solve for a triangle. We do remember a few things. We know that the sum of the angles for any triangle is equal to 180 degrees. We know the Pythagorean theorem, and at some point we should have seen this, something that says the sine of angle theta is equal to the opposite over the hypotenuse, where that is for a right triangle. This is the adjacent side, this is the angle theta, this is the hypotenuse, and this is the opposite side. So the sine of this angle is the opposite divided by the hypotenuse. Cosine theta is equal to adjacent over hypotenuse, and the tangent of theta is equal to the opposite over the adjacent. Okay, so those are the three things we really need to know to solve for triangles. And again, it's kind of a leap to jump from here to say that that's a triangle. But again, we'll save that for another day and it will be clear later. Let's work an example. We have x, we have this as 40 degrees, and we have this as 15 feet. Can you solve for x? And we look at this, so our options are sine, cosine, or tangent. Looking at the sides, we know that we have the adjacent, we have the angle, and we're looking for the x, which is the opposite side. Looks like tangent will be our best friend. So the tangent of 40 degrees is equal to the opposite, which is x, over the adjacent, which is 15. So x is equal to 15 multiplied by the tangent of 40 degrees. So from our calculator, we would say 15 times the tangent of 40 degrees. By the way, with your calculator, you need to take a very close look. You see this right there? You might just be able to make that out. It's a D. It says that we are in degree mode. You have to be careful with that because sometimes you get into radian mode and your answers will be all very different. If we hit equal there. So x is equal to 12.6 feet. Other thing we might want to do to solve this triangle is to say that this angle here is 180 degrees minus 40 degrees minus 90, where that 90 comes from the right triangle. This angle is then 50 degrees. We'll do one more example and then we'll call it a day. This time we have our triangle, angle theta, 12 and 4. We can use the Pythagorean theorem. A squared plus b squared is equal to c squared. So c must equal the square root of a squared plus b squared. In this case, that's 12 squared plus 4 squared. So c is 12.6. Let's try that in the calculator. So 12 squared plus 4 squared equals, then take the square root of answer. And that equals 12.6, just like we wrote there. Moving back, this equation is again our friend. Let's see if it works though. So we say the tangent of theta is equal to 4 over 12. So tangent of theta is equal to opposite divided by the adjacent. And this is the point where people really get stuck. Because what you need to do is you need to break theta out of the jail here. How do you get it free from tangent? And one answer to that is you use the arctangent or tan inverse, so tan -1 of tangent of theta, right? Whatever you do to one side, you can do to the other. We run it through this machine, tan -1 of 4/12. And when we do that, we end up with theta is equal to, let's work that on our calculator. So we have the inverse button, which is here. That little light will come on in that corner. So inverse tangent of 4 divided by 12, close paren. And that is equal to 18.4 degrees. Now I want to tell you a story. I want to tell you a story about these inverse functions. Because people always forget this. How do you take the inverse tangent of tangent and get theta? What I'm going to do is I'm going to get the best math book in my inventory. And I shall start to read to you. And it goes something like this. Not patronizing. This is real, guys. This is the best way I know to explain how this function works. Are you ready? Here it goes. Now, the star-bellied sneetches had bellies with stars. The plain-bellied sneetches had none upon theirs. Yes, Dr. Seuss. We're going to use Dr. Seuss to explain what we mean by this inverse tangent function. Maybe you remember the story. So here is the star on machine. So you can see the sneetches going in and they come out with stars. And here's the star off machine. Well, let me tell you about the star on machine. That's this one here. The sneetches go in and they get a star put on their bellies. Mathematically, we would say this machine, this yellow machine, is called f of x. And when you go in, you get a star, right? It's a machine, f of x. You could say f of x is equal to x plus 1. Not to be confused with the star off machine, which is known as g of x. And that g of x is x minus 1. So you go in with a star, you come out with none. Are you with me so far? Let's go back and write this down before we forget it. We described a star on machine, and we said that that's f of x is equal to x plus 1. And we had a star off machine, and we said that was g of x is equal to x minus 1. All right, well, that's not so bad. We can remember that. One machine to add a star, to add 1, basically, and one machine to take off a star, or to subtract 1. Going back, if you remember the story, what was the story? Let's see if we can read that part of the story. Let's see, I gotta find it here. Belly stars are no longer in style, said McBean. What you need is a trip through my star-off machine. This wondrous contraption will take off your stars. You won't look like sneetches who have them upon theirs. Well, then something about snoots in the air. Here it is. This is when things got crazy. All the rest of that day on those wild screaming beaches, the fix-em-up chappie kept fixing up sneetches. Off again, on again, in again, out again. Through the machines they raced round and about again, changing their stars every minute or two. That's this picture right here, isn't it? So you've got them, these silly sneetches running into this machine, coming out running into the other machine, and they're just going round and round and round and round and round. Oh, here, somebody's even done, is that Legos maybe? Here they go. They go in, they go out. They go in, they go out. So it turns out that you can chain these machines together, right? You can make it a circular process if you want. You could have the star off machine feeding the star on machine, or the star on machine feeding the star off machine. But the thing is, either way you do it, you come out the same, don't you? Right? So if you went into the star on machine and got a star, and then you went to the star off machine, you'd come out with no star. So you could say that you end up with x. Let's see if that makes any sense. One way we could do this is we could take the output of g of x and feed it into the f of x machine. So that would look like this. So we have the f of x, so we need to substitute that in right there. So we would say x minus 1. So there we just substituted g of x, right? We substituted that in there. Plus 1. Right? And we solve for that, and the answer is x. So f of g of x is equal to x. We could do it the other way around. So now we're flipping the star on and the star off machine. So g of f of x, let's see if we can figure out that one. So this time, we're taking this and we're running it through there. We're substituting, so we say x plus 1 minus 1 is equal to x. Well, isn't that nice? It doesn't matter which way you do it. If you run through the star off, then the star on, or the star on and then the star off, you still come out a sneech with whatever you went in with. Oh, that makes your head hurt, doesn't it? However, if we go back to this tangent function, and I told you that tangent and tan inverse are the star on machine and the star off machine, does that make it a little easier for you? So if you have the star on feeding the star off machine, you're going to end up with the theta that you started out with. You can play with that on the calculator. Let's say you had 30 degrees and you took the cosine of it. Whoops. So say cosine of 30 degrees. There we go. And now if you took the inverse cosine of that, you would get, whoops, inverse cosine of answer, you would get 30. Well, that was kind of neat. So those two functions undo each other in the same way the star on and star off works. Which is nice, because now when we come back here, when we want to break theta out of jail, all we have to do is run it through the star off machine, and we're all set. There it is. Inverse tangent of tangent gives you theta. And remember, if you can run one side of an equation through a function, you can also run the other side. And that's where over here we have inverse tangent of 4 over 12. And when we solve for that in the calculator, we get theta is equal to 18.4 degrees. I hope you liked it. That was my trigonometry story. That day, all the sneeches forgot about stars and whether they had one or not upon theirs. By the way, if you have kids someday, the absolute best story ever is in this same book, and it's called What Was I Scared Of? Well, I was walking in the night, and I saw nothing scary, for I have never been afraid of anything. Not very. Be safe out there. Have a good Labor Day.